All right, hello there. All right, today we want to talk about chemical reactions. Now, I'm going to tell you there's going to be a few things in this presentation that will be a little bit smaller. So I would definitely, if I were you, I would want to have my notes open as well so that I could follow along. But here we go. Let's talk today about chemical equations, and let's learn some principles on how to balance chemical equations, because obviously we don't want to lose sight of the big picture, and the big picture is the law of conservation of mass, law of conservation of matter. You know, we've talked about this before. We live on a planet where we don't destroy matter. Now, we can change its form, whatever the case may be, but we don't destroy it, so it has to be accounted for. All right, so here we go. Let's begin. In a chemical reaction, one or more reactants, change into one or more products. So what I want you to be thinking about right here, right off the bat, is that if you have a chemical equation, and we'll look at some here in a moment, you're always going to have what we call reactants, and you're always going to have what we call products. And ultimately, if we do a balanced chemical equation, we will illustrate how we have preserved the amount of atoms on both sides. Okay? All right, let's continue. You know that earlier in this class, we talked about chemical change and we talked about physical change. Well, if I had rusting iron, which is what I have here, then I would definitely have an example of a chemical change, because as we know, rusting is a chemical change. So what if I wanted to represent this with what we call a word equation? And I'm going to be honest with you, we're going to mention this right now, and then we're not going to use many word equations. This is going to be about us learning how to use chemical formulas. But here we go. So could I have what we call a word equation? And the answer is yes. I could simply state, by terms or by names, I could state the reactants and the products. For instance, I could say that iron and oxygen under the right conditions will produce iron 3 oxide. Well, what I'm telling you is that it will rust. But instead of using chemical formulas, I'm using words or word equations. So sometimes we do that. Sometimes we talk in that way. But obviously, this doesn't show us much in terms of individual atoms, and it doesn't really show us much in terms of the conservation of matter, okay? All right, so word equations can be good sometimes, but they could also be, and you can tell that looks cumbersome. You can tell that, they would probably at times be very cumbersome. It might be a lot more advantageous for us, and maybe quicker to the point, to use chemical formulas, okay? So today, we're going to talk about chemical equations, and we are going to utilize chemical formulas like H2O, NaCl, you understand what a chemical formula is, to represent a chemical reaction. Now, the second part of this series, not in this lecture today, but we'll actually talk about different types of chemical reactions. But right now, we're just simply talking about chemical reactions as a whole, and we want to use chemical formulas in our chemical equations, okay? So what would an example be? Well, I also teach biology, or have taught biology, so a very famous chemical equation that always comes into my mind is the chemical equation for photosynthesis. And it involves light, it involves chlorophyll, plants, you have carbon dioxide and water, you produce glucose, and the plant gives off diatomic gaseous molecules of oxygen. Okay, well, here we go. This is also a balanced chemical equation. So I would like to point out two things. I would like to point out, number one, that it is kind of a neat example of a chemical equation. But number two, this would actually be a balanced chemical equation, meaning that how many carbons we have over here would be reflected here, hydrogens, oxygens, so on and so forth. The numbers of atoms that we have would be reflected equally on both sides. But this would certainly not be a word equation. This would be a chemical equation utilizing chemical formulas. Okay, so what we want to learn how to do is we want to learn kind of the ins and outs, and we want to kind of learn, how to balance them, or what it means to balance them. All right? Okay, now before we go any further, and this is an example where you might have to look in your notes because this might be a bit small for this presentation, But let's talk about some symbols very, very quickly. Let's talk about this plus sign. Well, what is a plus sign going to do? We're going to use a plus sign to separate our reactants, and we're going to use a plus sign to separate our products if we have multiple reactants and multiple products. What about this arrow? Well, typically that arrow means yields. Remember, this is a reaction that is taking place, and by the virtue of being a chemical reaction, what you have at the end will be different than what you had at the beginning. That's one of the hallmark traits of a chemical reaction, okay? So the arrow would be yields. Now, sometimes that arrow will be bidirectional, which means that the reaction is reversible. And actually, this is a perfect example. You know, your biology teachers that taught you that as you go this way, it's photosynthesis, but as you go this way, it is respiration. That's how plants and animals kind of go hand in hand. All right, sometimes you'll see a little S in parentheses, which means solid, a little L, liquid, a little G, which means gas. So it's referencing the state of matter. Sometimes you'll see this little AQ. That means aqueous, okay? That means that the substance is dissolved in water, okay? Sometimes you'll see a little pyramid above the arrow. That infers heat, okay, is supplied to the reaction. And sometimes you'll see some type of little formula written above the arrow, which might be or could be an example of a catalyst, something that speeds up a rate of a chemical reaction. You probably remember studying about that in biology as well, but a catalyst can help a reaction proceed more quickly. So these are just some simple items that you might see in chemical equations, okay? Don't forget, we can definitely have a bidirectional arrow. It still means yields, but it means yields in both directions. Okay, the reaction can proceed one way or the other. All right? Now, sometimes, and you know, probably not a lot once we get going, but every once in a while you just see something that is referenced as, it's just called a skeleton equation. Well, come on, you've heard the expression bare bones. All right, so what's the problem? You know, what's the good thing and what's the problem? Well, the good thing is, you know, obviously we have some Fe2O3 here, which is our product, and we know that it took Fe and O in order to make that, so we kind of have an idea of what's involved. You know, the problem is that it's unbalanced. So while it gives you some information, it doesn't necessarily tell you the full story. So sometimes, you know, we use skeleton equations just to talk about bare bones, you know, kind of points or material, but often we would prefer to have a balanced chemical equation. But this would be an example of what we call a skeleton equation. So you would know what's in it and you would know what you have. And don't forget, and honestly, you might not even have the S, the G, or the S here. It might even be more bare bones than what I have here. It might just be simply the elements and the product, you know, the reactants and the product. But you know that S is a solid, G is a gas, and S is a solid, okay? And you know some of these other items because we just went over it. But this would be an example of what we would call a skeleton equation. Now, our goal in this lecture is to get past skeleton equations and to actually be able to balance chemical equations. Okay, so this would not be our desired goal at the end of this lecture. Okay, so you have a textbook that we use occasionally in class, and they kind of had a little example that is kind of a simple example, but yet I thought it was kind of poignant. They're trying to get you to understand in this example, what does a chemical formula represent? Now, I'm not talking about the whole chemical equation right now. I'm just talking about an individual chemical formula. What does it represent? Well, it represents whatever your product is, okay? So they gave you an example of a bicycle. And they asked you to look at the bike, and obviously you look at the bike and you can see that it has two wheels, it has a frame, it has a seat, it has handlebars, it has two pedals. But honestly, if you don't have those things, then, you know, I don't mean to be silly here, but you don't have a complete bike. So when you look at the chemical formula for the bike, well, what did they come up with? Well, they came up with FW2HP2. Now, I'm guessing that if you'll use a little common sense right at this juncture, you can guess what the F is. Well, the F is the frame. Agreed? What is the W? Well, you're like, oh, well, it's 2 wheels. That's why you have this subscript 2, because you have 2 of these. So that's what this tells you. Now, the absence of a number is not the absence of a number. It's just understood to be a 1, okay? Well, what's H? And you're like, well, that's handlebars. Yes. What's P? Oh, that's pedals. Yes. So what was their chemical formula for a bicycle? It was FW2HP2, right? 1 frame, 2 wheels, 1 handlebar, and 2 pedals. So in order to get the whole product, now listen to what I just said, in order to get the whole product, this was the chemical formula to give you this product, okay? Now, if F doesn't have a written number in front of it, then what is that understood to be? Well, it's just understood to be a 1, okay? All right? Now, what are the numbers in front of reactants or products called? And honestly, you didn't have any numbers in front here. So really, you didn't see that here, but I'm telling you right now that sometimes you do have numbers in front. Now, I also want to add a little note here, give you a little food for thought. If you have a number in front, you're going to multiply it all the way through, okay? But that number in front would be called a coefficient, all right, if you had a number in front. And we'll look at that here in a second, so just stick with me and just continue to listen, all right? Now, let's take H2O, for example. If I had the 2 as a coefficient, okay, so if I had a 2 as a coefficient based on what we just said, so I would put a 2 in front of this H2O, then how many hydrogens would I have? Well, I would have 2 times 2, so I would obviously have 4 hydrogens. I would have 2 times 1, so I would obviously have 2 oxygens. So think about that if you would, and sometimes maybe you need to stop and rewind or ponder a little bit, but I'm asking you if I had a 2 in front of the H2O. And sometimes you see that, and you will use coefficients to balance chemical equations. Once again, don't be big picture people. What do we want to do in this lecture? Ultimately, we want to balance chemical equations, so we will use coefficients. If a chemical equation has the same number of atoms on both sides and it shows conservation of matter, it is what? It is balanced, okay? If I have the same number of atoms on both sides, then I consider that equation to be balanced, and I'm done, and I'm finished with it, okay? And it would be a complete balanced equation. Now, I'm going to read 5 rules to you. You're going to have these in your notes. You're going to look at them. You're not going to grasp every single one of them right off the bat. You're really not going to really start grasping them until you start practicing, and I will give you some practice on balancing chemical equations. You know that I will, and we'll go over them together, but here we go. Okay, you need to determine, number 1, the correct formula for the reactants and the products. This is pointless if you don't have the right formulas in your reactants and products. Number 2, you're going to write a skeleton equation, okay? You're going to separate the reactants and the products with a plus sign, all right? So you're going to have a skeleton equation, and as you know, the skeleton equation will be bare bones, so it will not be balanced. You're going to determine the number of atoms of each reactant and product, and you're going to make sure that it is balanced. That is the key. You are going to make sure that what you have on the left side is what you have on the right, or vice versa, okay? You're going to make sure that you have the same amount of matter. That's what balanced means, okay? All right, you're going to balance your elements one at a time. Now, I'm going to be honest, and here it goes. Some of these are easier than others, and some of them are more difficult, and you're going to kind of develop your own method or plan of attack, and you'll get to where you're pretty good at it, but every once in a while, you'll find one that'll be kind of frustrating. And honestly, it's kind of like, it's honestly kind of like working a puzzle sometimes. But the reality is don't get like dismayed, because it's honestly just making numbers balance out is what it ultimately amounts to. And you'll be able to do it, trust me, okay? You're going to use coefficients in front, but you never change the subscripts. You do not have permission to create matter where matter does not exist. So if you have H2O, you could put a number in front of H2O, but you can never change that subscript, okay? The subscripts can be multiplied and so on and so forth, but you don't get to change them, all right? And then number 5, you're going to make sure that all your coefficients are the lowest possible ratio. In other words, if you had 2 and 5, okay, and now that wouldn't be a good example. Let me put it to you like this. When you're looking at your numbers, your subscript numbers, your ratio numbers, sometimes you'll have to make them balance out, but when you make them balance out from each side, you want to find the lowest common multiple. And I'll show you what I mean here in a second. So you're going to be looking for lowest common multiples. Maybe that'll make more sense to you. Okay? All right, so here we go. So what do you mean? Okay, I mean, because you can have a lot of talk, and talk is cheap until you put it into practice. So here we go. Going back to our first example of iron rusting. So if we had our sort of basic skeleton equation, we would know that iron and oxygen are involved, and we would know that this iron 3 oxide that we were talking about is our product. Okay, well, here's where I'm going to do something. All right, because here's what I want you to realize. And I think that you will realize this. Look, how many irons do you have right here? Well, you have 2. Well, how many do you have here? You only have 1. So that alone tells you right off the bat, this is not a balanced chemical equation. Okay, there's no way it's balanced. So your desire is to make sure that whatever you have over here is equal to what you have over here. Okay, you don't just get to lose something. You don't just get to gain something. We don't just go poofy and stuff disappears, or poofy and stuff appears. All right? Whatever you have over here will be equal to what you have here. And in this case, we know that these are our reactants because our arrow is going this way. So how are we going to attack it? Well, so, one of the ways to attack it, you got to start somewhere. So let's say we start with iron. And we say, okay, we have 2 here, but we only have 1 here. Well, what if I put a 2 in front of the Fe? Okay? Well, what would that do? Okay? Well, the question is, would that equal my irons? I have 2 here and I have 2 here. So yes. So wow, in one fell swoop, it looks like we're starting to make some progress. But what else do we need to check out? We need to check out our oxygens. Well, when we check out our oxygen, we have 2 here, but we have 3 there. So now we're like, well, that's not going to work. So when we look at oxygen and oxygen, this goes back to when we were making compounds earlier in Try A. Come on, how do you find the lowest common multiple? No secrets here. You just multiply them together. So the lowest common multiple between these two is going to be 6. So what are we going to do? Well, here's what we could do. We could say, okay, we have 2Fe plus, what if I make this a 3, okay? And what if I put a 2 in front of this, right? Remember, because I have to put a coefficient in front of, okay, that molecule, right? And then I multiply all the way through. So now what would I have? Well, I would have 6 oxygens, and I would have 6 oxygens, but I now have 4 irons, but I only have 2 over here. But that's where you're like, oh, winner, winner, chicken dinner now. That's easy because iron is isolated by itself. So that's an easy fix, Mr. Day. Yes, that's an easy fix. I just need to make sure that I have 4 of them. Now, here's the $1 million question. Have I balanced this chemical equation? And the answer is yes. I have 4 irons and I have 4 irons. 2 times 2 is 4. Remember, your coefficient gets multiplied through. So if you have 2 of them already, you're going to multiply 2 times 2. So I have 4 here and I have 4 here. I have 6 oxygens here and I have 6 oxygens here. So the question is it balanced? The answer is yes. The answer is this is a complete chemical equation illustrating both the reactants and the products. Now, I could probably go one step further and tell you what state of matter they are, like whether they were a solid or a gas or a solid or whatever the case may be. But in terms of balancing this equation, it is now balanced. All right? I will give you a second example, but I'm going to tell you the truth. The second example that I have in my notes right now is really pretty darn similar to the first. It involves a thin coating that aluminum gets on it called aluminum oxide. And so, in part, I sort of provided the same because maybe you could follow your own thought process now. But what I'm going to do after I share this example with you is I'm just going to provide some practice to you. And you can watch the lecture, you can look at the notes, and you can think about the rules. But what it's really going to, the rubber is really going to hit the pavement when you start trying to do the practice problems. Okay? I'm just trying to give you a fairly brief introduction. All right, so you look at this and what do you say? You say, well, okay, we're not balanced. We can tell. This is a very similar, in fact, almost identical, right, to the last problem that we did. So what are we going to do? Well, we're going to attack it the same way we attacked it before, and so hopefully you'll be like a step ahead of me now. You're going to say, okay, well, what if I wanted 2 aluminums? Well, I could put a 2 in front of the Al, okay? But the problem would be the same problem we had before. My oxygens are not balanced. Well, what's my lowest common multiple? Once again, you're like, oh, it's 6. Yes, it's 6. So I'm going to put a 3 in front of that and a 2 in front of that. But then that unbalances my aluminums. But since my aluminum is isolated, and you got to be loving it when things are isolated, but since it's isolated, I can just simply make that a 4. And so you're like, oh, okay, well, I may not be an expert, but I think I see the basic idea behind balancing chemical equations. I simply want to make sure that what I have on one side is equal to what I have on the other. And I'm really doing that with the use of coefficients. Yes, you're doing that with the numbers that you're putting in front of the molecules, because you do not have liberty to change the subscripts. The best thing for you to do right now is to jump in and do some practice.